All right, so Pre-Calculus 30. We're working from the Pre-Calculus 12 textbook, McGraw, Hill, Ryerson, and we are on page 62 for those of you that want to follow along. Have your textbooks open to that. We're starting chapter 2, and chapter 2 is about radical functions and transformations. So we're going to talk today from 2.1 about those two things. Radical functions are where we want to start. All right. So you know what a radical is from the last few math classes that you've taken. A radical is some kind of root, either a square root or cubed root or fourth root. It has some kind of root. So this is a radical equation. And if we were to graph that, that would be a radical function. All right. So we're going to take a look at radical functions. We're going to take a look at how the values of radical functions compare with other functions, and specifically how this compares with y equals x. Are you guys seeing that? All right, so you can write down as much of this as you want. I'm going to go through it step by step. I will just kind of skip down to the definition that's in your textbook right now of a radical function before we explore it too much further. So a radical function is a function, as I mentioned, that involves a radical with a variable in the radicand. So this is really important. There has to be a variable in the radicand or a variable underneath the root sign in order for this to be a radical equation. If you consider something like this, y equals x plus the square root of 4, that's not a radical equation. That's not a radical function because the x isn't under there. Okay? This is just a number. That's exactly the same as y equals x plus 2. So you have to have the x or an x, doesn't have to be the only one, but the x has to be underneath the radical sign in order for it to be considered a radical function. Okay, I hope you can see that. So that's point number one. We're going to graph these radical functions. We're going to talk about domain and range as well. What we notice right away about the domain, and I have that written over here, is that if we have y equals the square root of x, we know that we have real problems with taking the square root of anything that's negative, right? So we cannot take the square root of a negative value. Therefore, the function y equals the square root of x is not defined where x is less than 0. So right away, we know that for your regular old y equals square root of x function, the domain is restricted to anything that is 0 or greater. So x has to be 0 or greater. So that is x is greater than or equal to 0. All right. Okay, so the first question I have here that we're going to, how we're going to explore radical functions and of course the transformations that are connected to radical functions, right? We're going to talk about the radical functions and the transformations. And what you're going to see is that what you've learned in chapter 1, and you spent a lot of time focusing on transformations in chapter 1, for all kinds of functions. Well, the transformations, the parameters, they're all exactly the same for radical functions. Okay, so there's not a lot new to learn here when it comes to the transformation parameters. Those are all the same. All right, so question number one. How are the functions of y equals x squared and y equals the square root of x related? And for this, I'm just going to flip over to Desmos here. Where's my Desmos? Up over here. All right. Okay, so in Desmos, and again, you don't have to copy this down. You don't have to. You can just watch. But what I'm going to do is I'm going to light up y equals x here on our graph, right? So y equals x, where each point on this graph, the x and the y are exactly identical. That's the y equals x line. And this has been important for what kind of functions? That y equals x line, we just got finished studying what kind of functions that has a reflection about the y equals x. Inverse, right, in chapter 1. All right, so y equals x squared looks like this, okay, the red graph. That's a parabola. And here's y equals the square root of x in blue. Now notice that the domain is restricted. There is no graph where x is less than 0. It starts at 0 and moves forward. But if we focus in, okay, I'm going to zoom in now. If we focus in on just the first quadrant, what do you know? Oh, that's not how I'm focusing, sorry. What do we notice about that first quadrant? This is just, okay, give it some time. What do we notice about the first quadrant there when it comes to what we've just studied? Like this blue graph And this red graph right here, from what you see, they are what of each other? Okay, one is a reflection about the y equals x line, which means that they're inverses of each other, right? You mentioned that before, inverses. So that's interesting. That's very interesting. If we take a look at these two functions, then for at least part of the domain, they are inverses of each other. Okay, so really quickly, if we just focus on the domain is greater than or equal to 0, y equals x squared, if I were to flip around, these variables and solve for y, I have y equals the square root of x. And just the positive version, so they are inverses of each other, and as we've just shown, okay, with the Desmos there, right? So they're inverses on a restricted domain. Okay, well, that's great. That's interesting to know. What about how are y equals x and y equals the square root of x related? So I want to talk about that. And we have those graphs up on Desmos. So let's go back there. So I'll take away the x squared and I'll just show you these two. All right, so now you're saying, well, they don't look related. Well, what do we notice about these? I notice that there's a point right here that's on both graphs, 0, 0. And there's a point here that's on both graphs as well, 1, 1. Look at the nature of these two, okay? These are exactly the same except that y is defined as the square root of the x value for the blue graph, not just the x value. So that means that each y value on this graph, the green graph, each y value, we take the square root, okay? We take the square root of the x to get the new y value. All right, so let's go back to our notes. So if we compare, so what I'm getting at is we compare these two, right? What you do is you take the square root of the x. That's how y is defined. So if we use the little table of values, let's just do that. X and y, little table of values for y equals x, and little table of values for y equals the square root of x. So y equals x, we know that we have 1, 1, 2, 2, etc. Over here, if I take 1, the square root of 1 is 1. So we just saw that 1, 1 is on both of these graphs. Okay? And what about this? 2, 2 is on this graph. How does it change here? Well, if x is 1, y then is the square root of 2, or about 1.4. Right? So the square root of 2, let's see here. Square root of 2, 1.414. Okay. If we go back to our graph, x equals 2, I'm going to have to zoom out a little bit. Here's x equals 2. Can you see that right here? There's the point 2, 2. If I take the square root, or y equals root x, then this value drops to here 1.4, or 1.414. Okay? You guys good? Question? You good? Okay. All right, so literally what we do is we take the y value and square root it. That's how we get the other y value. So think about that. Let's zoom out a bit more. Look at this one. Y equals 4. X equals 4, y equals 4. So this one is x equals 4, y equals 2. So in order to get the graph, you take really the y value and square root it from one to the other. And I know I said we take the square root of x, but that's when we start with x equals the y value. So when you have a graph, you take the square root of the y value, and that is your new y value for the other graph, for the root graph. I don't know if that's making sense. So if this is, let's see, that's 6 there. Then what's the square root of 6? Can someone just punch that out in the calculator real quick? What's the square root of 6? So what times what will give us 6? 2.449. Okay, so look at this. This point right here, 2.449, is the exact square root of 6. Okay? Any questions there so far? Okay? All right. Okay. Let's go back to Desmos, and I want to show you this. Now I'm going to, I guess I could leave y equals root x up there. What I'm going to do over the side, if you can see this, this is y equals the square root of x, and I'm going to change the different parameters a, b, h, and k. Okay? And I'm going to show you, actually, I'll just move this h. I'll move this h up there. Okay. All right, so what happens if the a value, and I've got this dotted, I do have this dotted, okay, and here's the y equals x line. So this is the graph that we just saw, okay? So if I change a, what do you think is going to happen? What do you think is going to happen to this graph if I change the a value? If I increase the a value, what does a do to a graph? What do you know about that? It's a vertical stretch, right? So if I increase a, I'm gonna have watch this. Say so the blue line is just y equals square root of x. If I increase a to 2, every y value has been multiplied by 2. Every y value has been multiplied by 2. You see, it's gone a vertical stretch. So the a value here, if I change the a value, it still stretches the graph vertically. If I bring the a down, it compresses it. If a is negative, it flips it. Okay? So a does the same thing to this kind of graph right here. That's what it looks like as it changes. All right? So that's a. What about b? What does b do to a graph? What did we learn? It's a horizontal stretch, right? So it either stretches it out horizontally or it compresses it horizontally. If b is greater than 1, it's going to compress it. Now, this looks very, very misleading. This looks like the same as a. But remember, a and b can kind of cause the graph to do similar things. But what's happening with b is that every point here is moving in horizontally. Okay? So if b was 4 exactly, this value of 4 here should be compressed to 1. And so there we have exactly 1. Okay, so it's being compressed by 1/4 if b is 4. So it's actually compressing horizontally. Okay. Now, if it's negative, remember it flips over to the other side of the y. Okay, so that's b. And then, of course, h and k, straight slides, right? Translation sideways. If we move h, it just slides it sideways. If we move k, it moves it up or down. All right? Now, if we combine these transformations, this is what it might look like. Okay, we might have a transformation that looks something like that. Yeah, I know, crazy, huh? Oof, wow. All right, so we've got reflections, we've got stretches, we've got movement here. In this case, a is 1.6, it's been pulled up. B is negative, so it's been I guess the way you're looking at it, it's been flipped this way. And because b is greater than 1, it's also been compressed in a little bit. H is 1.8, so it's been moved over to the right, 1.8. And k is 2.6, so it's been moved up 2.6. And that's what that transformation might look like. Okay? So now that we've kind of explored those parameters, the same as what we've learned before, you can jot this down if you want here. All the same transformations can be applied to the radical function, y equals square root of x, if that's a base function, according to the same parameters in the same way. So y equals a, guys, do you want to jot this down? Square root of b, make sure you include your brackets in there, x minus h plus k. All right, so here's an example we're going to work through. Basically, what we're doing is we are graphing or sketching the graph of this function right here. Y equals 3 root negative x minus 1. Okay, so you can see in there that we do have just y equals square root of x. That's the root, the base function. And sometimes I refer to that root base function as the mother function, which my students have always really loved when I say mother function. But anyways, no. Is there a song? There is not currently a song about the mother function. Oh, I just broke my pen. That is not good. Wow. I'm going to have to pause and cry. All right. So the pen is fixed. Okay, good. So the mother function is y equals root x. And we've applied parameters to it, so it's been stretched, looks like, because of this number right here. Now that is a. A is 3. A, of course, refers to or indicates a vertical stretch. Okay, so just to make sure you understand how to draw this y equals root x graph, guys, watch this. Remember, if x is 0, then the square root of 0 is 0, so that's why we have a point 0, 0. If x is 1, then the square root of 1 is 1. That's why we have this point over here. If x is 4, that's a perfect square. Root 4 becomes 2, so that's why we have a point 4, 2, right? I hope you're getting this. If x was 9, square root of 9 is 3, so that's why we have the point 9, 3. And of course, the line is filled in because the square root of 6, as we said, was what about what? 2.499? So there we are, 2.499 right there. So all of these points, you take the x value, take the square root, that's your new y value, okay? So that should be, hopefully you guys can do that. So vertical stretch, that means that every point, and we can just pick a few, the ones that are known here, get multiplied by 3. So this is a 1 right here. This right here is 1. So times 3 goes up to 3. You see how this kind of stretches up to 3. So that point rises to 3. 2 times 3 is 6. 3 times 3 is 9. So after this first transformation is applied, this blue graph looks like this. Okay, as best I can here, I'm going to connect the points. Wow. You guys all right? Oh, at least the lid was on. This time. Oh, I heard that's a grade 11 thing this year, is it? Oh, it's a grade 12 thing? Okay. All right. You guys are super cool. No, it's true. It's true. All right. So that's the 3. What other transformation do we have? What else has happened here? Well, if we look at the let's change the color. If we look at this negative, that's a -1 for a b value. So what does that do? That flips things horizontally. It's a reflection about the y-axis. So that means that this point right here goes over here. This point goes over here. This point, which is 9 units to the right, is actually over here 9 units to the left. So this graph after the second transformation looks kind of like this. Something like that. That's not the best drawing there. It's a little tough to do on this tablet. But anyways, you get the picture, right? It flips over. Finally, we only have one. This is the h, right? The h is technically +1 if it shows up as a minus. And so what this means is that we move everything to the right 1 unit. And that's where we get the final version of this graph. Everything is moved over 1 unit to get the purple graph. Notice that k is 0, so we do not have to move it up or down. All right? Capiche? Understando? You get it? Okay? Are there any other words for do you understand? Someone else help me? Huh? Vamula? Vamula? It's like formula, but formula. All right. Like I said, you guys are super cool. So, whatever you say. Oh, is that Portuguese?
No.
It is? Is it a bad word? Is that a bad word? Is that a bad word in Portuguese?
No, it's let's go.
Let's go? Like this? Let's go! Like you basketball players do? Like that?
No, that's in Nigeria.
That's Nigerian? This is Nigerian. This is Nigerian? So when you guys want to substitute in basketball, you're all speaking Nigerian? Is that what this means? Okay. Wow. Okay. Guys? Okay, we got to keep going with the lesson here. All right. Little comic relief there. So, method 2. Remember, there's 2 ways you can graph the transformed graph. Okay? You can do each individual transformation, which is great. Or you can do the mapping, the points directly. You remember this? So you remember mapping notation? So we've got an A of 3. Where's A? A, right here. So it's actually going to be 3 for A. What else? We've got a B of negative 1. So this is going to be 1 over negative 1. What else do we have? An H of 1. So it's going to be plus 1. And we've got a K of 0, plus 0. So if you plug your X and your Y values in here, then you can transform as many points as you want, and you can just immediately get the corresponding image point. So for example, 0, 0, let me just make some space here. So 0, 0, what does that turn out to be? Well, it turns out to be negative 1 times 0 plus 1. Negative 0 plus 1. 1. Comma, 3 times, this is 0, plus 0. 0. So 0, 0 becomes 1, 0. Let's just see. It started off as 0, 0, and in the final version, it's 1, 0. Look at that. Mapping notation might work. What about this? Negative 4 plus 1, comma, 3 times 2 plus 0. What's that? Negative 3, comma, 6. Let's check that out. Does 4, 2 become negative 3, 6? Well, 4, 2 on the original graph was this one. Does it seem to correspond to negative 3, 6? Let's see. Negative 3 up to 6. Boy, that looks like it could be the corresponding point, and that is on the graph. So you could take a few of these points, use mapping notation, and just bippity boppity boo, put her in there, and then you get the image points, and then look at this. You got an image point, you maybe want to do this image point, maybe another one, and you can just go ahead and sketch the graph. Whoa, that's really bad. You can connect those points and sketch the graph that way. Okay? I don't know what you like better. Mapping notation, sketching the individual, I don't know. But 2 ways you could do that. All right? What else do I need to tell you? Oh yeah, domain and range. So remember, for y equals root x, right, the domain is x has to be greater than or equal to 0. You cannot take the square root of negative numbers. The range is y is greater than or equal to 0 because it starts at 0 and it goes up and out. The domain and range for the transformed graph, you have to be very careful because there's those flips. So x in the positive direction could become x in the negative direction. You could flip down, so the range, if its y is greater than 0, could become y is less than 0. Okay? So after the transform function, you kind of have to have an idea. You have to examine it a little bit. You have to examine if a and b is negative, or if h and k moves up or to the right. So you have to take that into account. If you do this, the graphing stages like we just did, then you can see the final graph. Hey, the domain for the final graph is x less than or equal to 1. You see that? It's here and to the left. That's where the purple graph is. The range, because k, we haven't moved up or down, it's just been slid over, the range is still y greater than or equal to 0. So domain and range, you're going to be asked about domain and range. Okay? Pay attention to the positive, negative values for a and b, and the h and the k. That will affect the domain and range. Questions? Okay. All right. Don't have too much else here to show you, but I do have something in the textbook that I highlighted. Okay. Okay. Yeah, the one thing I wanted to address with you here is, just give me a second to find it. Okay, so if you look at these graphs here, okay, so here's just a couple examples of transform graphs. This graph has been moved to the right 2 units. This graph has been moved down 3 units. All right, but on, okay, page, okay, let's see if we can get to this now. Yeah, okay, this one here is what I wanted to show you. So this example, page 69 in your textbook, okay, it says determine 2 forms of the equation for the function shown. Okay, this is where it gets tricky, and this is the last thing I want to show you here today before I give you your assignment. Remember how we said that sometimes A and B can make the transform graphs look exactly the same? Or if you have a transform graph, how do you know if it's a stretch like this or a compression like this, right? Or how do you know that it's stretched this way and not compressed this way or whatever? So let's take a look at this. This graph right here is a stretched graph, okay? Determine 2 forms of the equation for the function shown below. This is a function that's been transformed from this original mother function, okay? This little mother function right here. It was like, okay. That's why I don't say it that often. All right. So we're gonna do this. We're gonna check and see if we can find out an A for this and or a B. Okay? So we might be able to write this, well, we can write this both ways. So this right here, okay, I'm going to sketch the original function 4, 2, 9, 3, and so on. Guys, stay with me back there. This is y equals root x in black that I'm drawing right now, okay? That's y equals root x. So it looks like this has been squished down. We could probably calculate this pretty easily, that it's been compressed. That is the A value. So if we examine this point with this point, that's a 1. This is a 0.5. This is a 2. That's a 1. This is a 3, sorry, and this is a 1.5? That's right. Okay, 3 and 1.5. Thing looks really weird here. Oh, I see. Sorry. This is 3 up here. My bad. Did you guys notice that? Probably not. All right. That's 3. I went to 2.5 instead of 3 there. Sorry. So it looks kind of like this. Sorry. So 3, half of that. Okay, so y equals 1/2 root x. That's what the blue graph is. Because we squished it by 1/2. Now my question is, how can I write this with a B value? How can I write this as a horizontal stretch? So remember, we want to think horizontally. Watch this. This point right here, where is the corresponding point on the horizontal plane? It's right over here. Okay? This is x equals 1. This is x equals 4. Okay? This one right here, where x equals 2, it's right about here. Okay, what's 2 times 4? Is 8. Look at this. That's where 8 is. That's the exact same y value. So we've multiplied both of these times what? 4. Times 4. So it looks like we can write it as a horizontal stretch by a factor of 4. Now, is B 4? Awesome. Awesome. B is 1/4. If it's being stretched horizontally by a factor of 4, then B is 1/4. Very good. Do you know what I want to highlight here? Are these the same? Are they the same? Well, check this one out over here. Root 1/4 x can be written as root 1/4 times root x. What is the square root of 0.25? It is 0.5. So actually, these definitely are the same functions. Oh, let's go! Vamos lá! Vamos lá! Wakanda forever! Okay. Get it? Okay. Oh, now we have a horse in the stable over there. Okay. All right. There certainly is more to this section. There are more examples that I think you should look at. But I would like you to sort of fast forward to the key ideas. Take a quick look at those, please. If there's anything in there that you do not understand or that I haven't covered this lesson, please ask me about it and I will give you your assignment in 1 minute. Okay, so the one other thing I will add to this lesson is a couple things. There's no right endpoint. There's an arrow here, right? Because you could take an x value of 1 billion and take the square root of that, and that would be the corresponding y value. There's no end, so that keeps going. The other thing is this shape, if you're wondering about the shape, of course it is a half of a parabola. So it's a parabola turned on its side because remember, if we were to reflect that, that would be, if you look sideways, that's a parabola. So this is not a straight line, okay? It's not sort of something crazy like this. It is a half of a parabola. So if you're wondering about that shape, that is a reflected parabola because here's the parabola that is, the inverse, the reflection. So it is part of a parabola. Okay, continue on with your assignments there from your text. And here's your text questions in case you've forgotten your textbook at home and you want to take a look at this video. You can see all of the questions here on the screen.
Okay, I'm going through it again where I'm not eating. It's not okay.
Oh yeah.
I'm like full. But it's not good because I have a game and I have to like I'm not even hungry. Yeah. Like really small. That's weird. Remember when we went to Sanskrit and I did not eat for 5 days? Yeah. And you were like, you have to. I'm like so hungry. Okay, I'm trying to. It's like forever. No, it's not.